Hello, welcome back to Mrs. Ogram's Maths. This is a worked solution video for level 3. It's the statistics paper from 2021 and it's for the probability distributions paper, which is standard number 91586. So for question 1, we have the situation of stopping at some lights along a stretch of road. We've got 6 lights and we need to justify the use of the binomial distribution. Now those keywords there mean that you're explaining why the binomial distribution fits this situation, and we will use our acronym of FIST. So that means there's a fixed number of trials, the trials are independent of each other, the success probability remains constant, there are 2 outcomes that can be termed as true or false. So I'll fill those in context now. So the fixed number of trials is that we have 6 sets of lights along Memorial Ave. That's not going to change. There will always be 6 lights. Each thing is independent of each other. So of those 6 sets of lights, being stopped at one light is independent of stopping at others. It doesn't make it more or less likely that the other lights will stop you. The probability of success remains constant because we will always have a probability of 0.45 of being stopped at each of the lights. And finally, there are 2 outcomes to each trial. So each set of lights, we will either get stopped or not stopped. Part 2, we're going to calculate something on this. So I use my notation. X follows a binomial distribution where our number of trials is 6 and our probability of success is 0.45. Or you could just write it as n is 6 and probability 0.45. So then if we are working out the probability that they're being stopped at none of the lights or all of them, that's the probability that x equals 0 plus the probability that x equals 6. We're going to go over to the calculator and use the tools that are in here. So stats menu, distributions, binomial. We are doing it at a point, so we want f1 for an exact value. We need to change this into variables because our calculator's been reset and it's thinking that the things are in there as a list, but we need to switch that to entering variables instead. So for x we have 0, number of trials is 6, success probability is 0.45. So we have 0.0277, we'll round that. And then we'll go back and we'll do the same, but this time putting in x is 6. And that's 0.0083. And that comes to 0.036. For part B, the probability is being changed from 0.45 to 0.6, and we want to calculate an estimate for the probability that a driver will be unlucky, which is meaning that they're required to stop for more than half of the 6 sets of lights. So we've still got 6 trials, but our probability has changed to 0.6, and we want to work out the probability that x is more than half of them, so more than 3, which is the same as if we do 1 minus the probability of everything that is up to and including 3. Because if we put it that way round, we can do it on our calculator. So we're going over to the stats menu, distributions, binomial. This time it's cumulative, so we want F2, we want everything up to and including 3. Switch it to variable because it had list. Now x is 3, number of trials 6, probability 0.6. So it'll be 1 minus 0.45568, which is 0.54432, or if we're going to round that, 0.544 would be sufficient. Okay, for part 2, there's actually quite a bit in this question. So we've got a person driving the length to work and back home. So I'm just going to kind of highlight these, to work and back, over a week, so Monday to Friday. So that means they're taking 10 trips altogether. We want to investigate the claim that they won't experience any increased likelihood of being unlucky. So we want to compare the chances of being unlucky before and after those safety changes were put in place. So before, let's look at the probability of unlucky. And that means that they had remember the before was we had a binomial distribution with 6 and the probability was 0.45. To be unlucky, it's the probability that we get stopped more than 3 times, which is 1 minus the probability that x was less than or equal to 3. And on that one, we just need to go back to what we had here, but the probability was 0.45. So the probability of being unlucky on one trip would be 0.2552. Now they take a total of 10 trips, so we want the probability of being lucky on every trip. So for them to be unlucky 10 times in a row would be 0.2552 to the power of 10, which I've just worked out over here, comes to this number here. Now let's compare that to after. So the probability of being unlucky we just worked out on this question up here. So that's 0.544 on one trip. So the probability of being unlucky on all 10 trips will be 0.544 to the power of 10, coming to 0.0027. Now we want to do a relative risk comparison. So making a comparison of those two chances of being unlucky, that division comes to 1,940. So this probability afterwards is 1,940 times as likely as the probability before. So let's put that into a sentence. So it's 1,940 times as likely to be unlucky on 10 trips after the safety changes are made. And then just go back to the question and check we have answered it. So investigate the claim that they won't experience an increased likelihood. Now we need to make a judgment against that claim. So we would reject that claim. Now, as it turned out for this question, they did accept an alternative sort of judgment being made. So at this point, if you look at these two numbers here, they're so tiny that in reality you're unlikely to experience a difference. So this bit here sort of comes into play, so that this person will not experience an increased likelihood. So they did accept that if people made the judgment that this is very small, this here is also very small, so it's unlikely that you would experience a difference in your likelihood of being unlucky. And if you made that sort of argument, then you would say that the claim could be justified. I prefer what I put here. It's got the maths behind it. I think that's the expected way to go about this question, but they did accept that alternative. And on to part C, pause to read. Okay, so we've got this graph here comparing the observations that are in the grey bars and then a binomial distribution for comparison. The theoretical values have been put onto the graph for some of the bars. And we're being asked to complete the graph by showing the remaining values for the theoretical binomial distribution model. So the missing ones are here on the 0, 1 and the 2. We don't need to bother up here on 7 and higher because the probabilities will be that close to 0 that it would be impossible to kind of draw on. But we do need to do it for the 0, 1 and 2. So we've got a binomial distribution. We had 10 drivers that were observed and the probability was 0.167 that they were using their phone while stopped at the traffic lights. So we will go to our stats menu again, distribution, binomial, we're doing it at a point. This time we've got the X number is 0, number of trials is 10, and our probability 0.167 gives us this probability for 0. So probability X equals 0 is equal to 0.1609. Probability that X equals 1. I'll just go back and change this 0 to a 1. And then the probability that x equals 2, same thing, change it to a 2. And we pop bars on at those heights. So we've got 0.1609 about there, 0.3225, let's say it's about here, and then 0.2901, so it's around about here. Okay, then part 2, discuss 2 features of the observed and theoretical distributions that justify the suitability of using a binomial for this situation. So we're looking for 2 things that are similar. So let's just go back and have a look. The obvious thing, since we were just calculating them, is to compare what the theoretical model came out with what the actual data did with the grey bars here. And we can see that they're quite similar. So we'll write something about that. We'll notice where there are some differences and then where there are similarities. So here's that statement. We've got some differences, but it matches really well for 3 or more. And where there are some differences, those differences aren't very big. All right, back to our graph for a second one. Now, things that are a little optional here as to where you go. I think including the comparison of calculations and the observed data is a must. So we've done that one. But from here, it's up to you what you choose to do. Now, when we're looking at distributions, we look at things like center, shape, any unusual values. So for this one, we can start by looking at what the center values are. So what's the mean and what's the median or the modal value. So mean we could work out if we wanted to. So the mean, if we were doing it on the binomial, we'd do 10 times the probability. And then comparing on the graph, we would work out 0 times the probability here, 1 times the probability here, 2 times the probability there, add it all up. That takes a little while. So I'm actually going to take the easier, faster option and compare the shape of the graph. So we can see that they both follow the same kind of shape, that they have this right skew going on, and they're fairly similar in their pattern of how that happens. So there's that one. And then finally, the last bit of this question, I imagine a lot of people will have missed. So we've discussed the 2 features, and then we need to discuss this word justify. So has this justified the use of the binomial distribution? And since we've said in our reasons that these 2 things were quite similar, it means the binomial model appears to be a good fit. Okay, pause to read question 2 if you need to, and we'll crack on. There would have been some kind of picture up here in the real paper, but it's not needed for the question. Okay, so use a suitable probability distribution to calculate an estimate for the probability that there are more than 4 wildling pines in any hectare on Rangitoto Island. So we've been given the probability of something happening within a given space. So that means it's a Poisson distribution. And our mean value per hectare is 1.8. We want to work out the probability that x is more than 4. So more than 4 will be 1 minus the probability that x is less than or equal to 4. And we'll hop over to our calculator. We want the stats menu, distributions. This time we're going across to Poisson. And it's cumulative up to and including 4. We want to change it to variable if it isn't already. X is 4 and our mean is 1.8. So we get 1 minus 0.9636, which is 0.0364. We consider it a success when the probability of finding at least 1 is 1/3. What parameter would provide this result? So now the probability of success is changing. We need to find out what that lambda value is. So we're told that the probability that greater than or equal to 1, so at least 1 is 1/3. Now that's the same as saying the probability of x equals 0 is equal to 2/3. And if we've got that, the probability that x equals 0 is e to the minus lambda. And then we can use equation solver to do the hard part for us. So equation solver, here we are going to do e to the negative lambda. So I will just use an, where is it? I was looking for L. It doesn't matter what we pick though. Ah, here it is. And that is equal to 2 over 3. And then solve. So lambda is equal to 0.4055. All right, part 3, we've got an area of 2,311 hectares. 100 hectares make up an area of 1 square kilometre. Provide 2 reasons why it might not be appropriate to use a Poisson model to do these sorts of things on a per square kilometre instead of the hectare measurement that we had. So for this, go back to that RIPS acronym, random, independent, proportional, and singly, and find 2 of them that you think wouldn't fit this situation. Okay, so I am going to go with the independence one because we're talking about trees spreading their seed. So if you come up with a wildling in one spot, you might be more likely to find more in that same spot that came from the seeds that were being distributed from the same tree. So there's my write-up of that. The other one I'll go for, I'm discounting singly because we can't have a tree that, 2 trees that grow in the exact same spot, so it actually would fit singly. We could talk about proportional and say that multiplying up by this scale might not quite work. I don't find that one as easy to talk about, so I'm going to go with the random one. So Poisson assumes that distribution is random, and that might not be the case because you might get differing conditions across these areas. So here's my write-up, and we've got this idea that there's more variation because this area is larger than what we started with. We're talking about 100 hectares. Within 1 hectare, it's probably the conditions wouldn't change all that much, and we could assume randomness, but not when we're getting up to this larger square kilometre area. Now, last bit to finish off is just to say that these 2 things don't match with the assumptions of a Poisson distribution. I've just squeezed that in there for both of them, try and fit it on the screen for you. For part B, we've got some information about the recurrence of these wilding pines after they've been cleared. We've got some information for the North Island and some for the South Island, and we're being asked to sketch those probability distributions on this bit of squared paper. Okay, so the important bits of information, right? North Island, it's likely to occur anywhere between 3 and 18 months. For the South Island, however, that's going to be anywhere between 3 and 27 months, and most likely at 12 months. So let's put that data onto the graph. So we need our amounts along the bottom to go between 3 and up to a maximum of 27. So there's our scale. Now let's start with the North Island. That goes between 3 and 18, and it can occur anywhere between. So if we take a look at drawing that one, I'm going to do that one in blue. So it's going to start at 3, finish at 18, but we need to figure out how high it goes. This will be a uniform distribution, so it's going to make a rectangle, and the base of that rectangle is 18 minus 3, so it's 15 along, so it needs to be 1/15 high. Now to help you sort of plot it out on the squares, this might be easier to think in decimals. So 1/15 is 0.06 recurring. So I've done a little scale where each square is going up in 0.01. So 0.6 recurring would come to around about here. Okay, and if you're sort of estimating where to draw something, then definitely write on the side what this value is. So it was 1/15 high. So we'll call this North Island. And then let's do the South Island in another colour. So the South goes from 3 to 27, but it's got a most likely time at 12. So for this one, we've got a triangular distribution because we've been told the mode. So 3 up to 27 with a mode at 12. So that'll be the mode just here at 12. And again, we need to work out how high it goes. Now you have got that on your formula sheet for the triangular distribution. It's 2 over b minus a. So that's 2 over 27 minus 3. And I'm just going to tidy up my b minus a. It's hard to see what that was actually saying. Okay, and so that makes a 12th. So a 12th in decimals is 0.0833. So let's take that height up from, the height will happen at 12, so it'll have a peak of 12 with a height of 1/12. So we're taking that up to 0.083 is around about here, and then straight line down to 3. Let me try get this one, straight line down to 27, and we will pop in there that the height was equal to 1/12. So this is South Island. Okay, part 2, calculate an estimate for the probability that a randomly selected area in the North Island and a randomly selected area in the South Island both see a re-emergence before 8 months after clearing. Okay, so back to our graph. Before 8 months, so that's going to be, here's an 8. Actually, let me do that in another color. So 8 is just here, and that's going to be our cutoff line where we're working out we want the area up to 8. So for the North Island, it's going to be the area of this rectangle here. So North Island, probability of being less than 8 will be equal to the base, which is 8 minus 3, so that is 5, times by the height of that rectangle, which is 1/15. So overall, it's equal to a third. For the South Island, the probability x is less than 3. For this, we need to just go have a look at what's happening with the triangles. So we want the area of this triangle here. And what I'm going to do is compare it to the big triangle here. I like to work with similar triangles. You can use the formula on the formula sheet. So the little triangle goes 3 to 8, so it's got a base of 5, and we need that height there so that we can work out its area inside. The big triangle goes from 3 up to 12 with a height of 1/12. So the base of this triangle is 9. So going from this one to this one is timesing by 5/9, which we would apply to the 1/12 as well. So h is equal to a 12th times 5/9, which comes to 5 over 108. I've just done that on the calculator over the side here. These aren't pretty numbers. So the area will give us the probability that x is less than 3 of that smaller triangle, that is. Oh wait, not less than 3. I should have fixed them. It was less than 8 on all of them. Whoops. Okay, so less than 8. So we have the area of that smaller triangle has a base of 5. We do half times the base of 5 times the height, which is 5 over 108. And that comes to 25 over 216. Now, make sure we finish the question. We want to calculate the probability of a randomly selected area in North Island and a randomly selected area in the South Island both see this re-emergence. So the probability of them both happening is going to be 1/3 times by 25 over 216. So we're just doing the probability of the North Island times the probability of the South Island, and that comes to 25 over 648, which is not lovely numbers, so let's turn that into a decimal. 0.0386. Now, I was about to say one thing about being able to do that times, but it's actually in the next question. So let's move on to that. So calculating this probability that we just did required at least one assumption to be made. Now, that assumption happened when we did this timesing. Probability of finding that both things happen can be done by doing a timesing if those two things are independent. So that's the assumption that we've made. Now explain whether it's likely to be valid. So we've assumed that the likelihood of reemergence is independent. I'm putting this into context now. Now, is that a good assumption to make or not? Think about what might have caused a reemergence to be more likely within the first 8 months. It's probably down to weather. Say there's like some good wind conditions that would spread the seeds, perhaps good sun exposure, that there's that these wildlings have had the right conditions to thrive. Now, comparing between the North and South Island, you could argue this both ways. You could say that they have different climates, but I would actually go with saying that they are fairly similar climates. So if we had a particularly good summer, then it would probably affect both the islands, and therefore the independence assumption doesn't hold. Okay, question 3. Okay, so we've got probability of buying extras for your computer, whether you're using System A or System W on these two different computer operating systems. Right, use statistical reasoning to explain what features of the distributions cause these similarities that were stated above and differences in expected values and standard deviations for the number of extras. Okay, so the similarity is that we have the expected value being fairly close to each other for both systems. Now, taking a look at the distribution, why do we think that would happen? So these values are 3.4-ish, so it's somewhere in the middle here. And if we look at the overall distribution, it is central to this 0 and 7 extremes. Now, looking at the probabilities, we've got them kind of small up to big, down to small again. And the system W has sort of big down to small up to big again. So if you were working out the expected value, that those, because they're symmetrical, they would both give us an expected value in the middle. Then the reason for the different standard deviations comes from the same thing. So because system A has its it starts small probability, big probability, small probability. So it makes like a hump in the middle. It means most of the values are close to the middle, whereas system W has its extreme things like the big stuff happening on the outside. So most of their stuff is away from the middle. So they've got a bigger variation. I'll just write that up. There you go. Now, that was an excellence question, which I always find the stats papers are a little bit mean. They often have excellence up front. But anyway, don't let it put you off of doing these papers. Just scroll through and find the bits that you can do first. You don't have to answer the questions in order. So, moving on to part 2. Compare the probabilities of buying 5 or more extras for system A and for system W. So 5 or more on system A. Let's go back to that table. We've got these 3 values here. So 0.08, 0.04, 0.02. And then on W, we'll do the same. And I've just done that quickly over here, so 0.47. We've been asked to compare them, so clearly you're more likely to buy 5 or more on system W than system A. Okay, for both system types, it's believed that the time taken for a serious system error to occur can be modeled by a normal distribution, and we've got the details for it. Okay, estimate the probability that a given computer from either system lasts for more than 6 years until its first. So if it lasts for more than 6 years, then it will also last for more than 7.5 years. Okay, so normal distribution, 5.5, sigma 0.9. We want, first of all, the chance it lasts for more than 6 years. So here's 6, we want more than 6. So probability that x is more than 6 on this type of distribution, we'll go to our stats menu, distributions, normal, cumulative. Our lower is 6, our upper is just something very big. sigma is 0.9, and then the mean is 5.5. That comes to 0.2893. We will also need the probability that it lasts more than 7.5. So probability that x is more than 7.5. Oh, that's bad. X more than 7.5 is equal to, go back to the same thing, but now it's going to be a 7.5. That's 0.0131. Okay, now we've got a conditional probability. The probability that it goes for more than 7.5, given that it's already gone for more than 6. So that's the probability of both of those things happening. So the probability it goes for more than 7.5 and more than 6, well, that means it's just the probability going more than 7.5, because those both things would happen there. If it's gone for more than 7.5, it has already gone for more than 6, and then divide it by the chance of the condition that we've applied. The condition is the bit that we have been told is a given, so that's the more than 6, so that's 0.2893. That comes to 0.0453. All right, another system experiences system errors within the first 2.5 years after purchase and more than 8.5 years. Total probability just over 4%. For us to justify if the normal distribution we were working with before would work for this system. So let's try it out with the 5.5, and sigma is 0.9. So find the probability of, so we're doing the system error less than 2.5 and then more than 8.5. So we want less than 2.5 here and more than 8.5 in here. So what I'm actually going to do is the probability between them and then just take it away from 1. So if we do between 2.5 and 8.5, that's going to have a lower limit 2.5, upper limit 8.5. Same things for the other stuff. That is equal to 0.9991. So probability that x is less than 2.5 and also more than 8.5 will be 1 minus 0.9991, which is 0.009. Now compare that to what we were given in the question. We were told the total of that would be just over 4% for this system L. So this is equal to 0.09%. It's nowhere near the 4% we needed it to be. So it doesn't fit. Right, we've got another company. This one is doing an operating system called System C. It's got the graph down here of the system errors that happen, and we want to go on and compare or justify being able to use a normal distribution to represent what's happening here for the errors on System C. So the first thing I'm going to look at is shape. When we're being asked to do normal distribution, is it a bell-shaped curve? And yes, it roughly is. We've got a little weird thing happening here, but most of all, this is a bell-shaped curve. Now, since we're talking about the mean and it being symmetrical around the mean, let's take a look at what's happening with our mean on our distribution. So our mean is 6.236, and the normal distribution given is 6.25. So that's pretty close. That kind of matches too. The other obvious measurement to check is your standard deviation. Now, on a normal distribution, your data should mostly fit within 3 standard deviations of the mean. So let's work that out. So 3 standard deviations away on our normal distribution, mean is 6.25. If we go 3 times 0.8 below and 3 times 0.8 above, we get a range of 3.85 through to 8.65. So let's look at the data we've got. Our minimum is 3.75, that's close to the 3.85, and our maximum 8.688. So that's pretty close to the 8.65 as well. Okay, one final thing to do for this question. You are always expected to calculate a probability on these things and make a comparison. So we could take a look at, because we've got the interquartile box here, that kind of makes you think about the middle 50%. Sometimes in these questions you get given a particular value of interest and you'd work out the probability of it being above that value. You could pick anything really here. You could do what's the chance of it being less than 5 or more than 8, or maybe go back to the previous question with that, the numbers we had there. But let's take a look at the central 50%. For no other reason than the box is there and it's easy to read off those numbers. Okay, so the central 50% on the normal distribution. So let's go over to our stats distribution, and we are doing an inverse normal. We want the center, an area of 0.5, and those values are still sitting in there from before. Oh, sorry, so we have to change them to these ones. So we want the standard deviation to be 0.8 and the mean is 6.25. Okay, so that's between 5.7 and 6.7. Compare that to the data, and we've got our 25% at 5.7 and our 75% at 6.7, so pretty close. And now we'll just finish with a statement that the normal distribution appears to be a good model.